Hello and welcome back to the Science of Concrete Materials class. This is lecture number 16 of the class, and we are still on the cement module of the class. In this part of the class, for the next couple of lectures, maybe 2 to 3 lectures, we will talk about the mineral admixtures, also known as the supplementary cementitious materials. And we will also cover the blended cements, which is the remaining types of the cements I mentioned previously when I talked about the cements types. So I deferred the talk about the blended cements after we discuss the supplementary cementitious materials, so it makes more sense for you. Okay, so in this class, in this set of lectures, basically what we will discuss, the SCMs. Why do we use them? Their types, sources, classification, their chemical composition, physical characteristics, what do they do for concrete, how they work, details of the most common SCMs, and how they impact the concrete properties. Not necessarily in that order, but these are the topics will be covered. Okay, so the addition of finely ground solid materials to concrete is an established practice in modern concrete technology. Collectively, these materials are called mineral admixtures or supplementary cementitious materials. Admixtures are added for a variety of purposes, with the mineral components being used primarily to replace cement. Okay, we add them to improve the workability of the fresh concrete or enhance the durability of hardened concrete. There are another class of admixtures, which is the water-soluble additions, referred to as the chemical admixtures. Those will be discussed in the second module of the class. So here's just a photo. It shows some of the mineral admixtures commonly used in the concrete industry. From left to right, as you can see here, we have the fly ash, class C, the metakaolin, which is the calcined clay basically, silica fume, fly ash, this is class F fly ash, slag, and the calcined shale, just to give you an idea how these materials look. Okay, mineral admixtures can be divided into three main categories. The pozzolanic materials. Later we will define what the pozzolanic material or what is a pozzolanic reaction, so that you understand the term. We have the cementitious materials and we have non-reactive materials. In Europe, basically commercial cements are always blends of Portland cement and mineral admixtures. But in the United States, such blended cements are less common, although they exist, but less common. It is more usual, for the specifications to require the concrete producer to add a material from either categories 1 and 2 above as supplementary cementitious material. In either case, though, the end result is the same in terms of the impact on the concrete properties. The mineral admixture basically interacts chemically with the hydrating Portland cement to form a modified paste microstructure. That's how it works. The use of mineral admixtures can be advantageous in several ways. We have technical advantages, such as improved durability, and as we will be discussed later at length, But many ready-mix companies, for example, use fly ash simply on economic grounds, since it is cheaper than cement. Economically, fly ash is cheaper than cement. Slag probably comparable to price of the cement, although a little cheaper. But silica fumes, for example, is much more expensive. Of course, it has a lot of benefit, as we will see later. Also, mineral admixtures are environmentally friendly. Not only because they are basically waste products turned into being valuable commodity, but also because of the energy consumption and the CO2 emissions associated with the production of cement, basically, or concrete as a whole. So basically, by using this, we are helping the environment. As I mentioned, and if you remember in the beginning of this class, I said one of our responsibilities as concrete professionals is to make the use of concrete more sustainable. That means less expensive by using alternative materials, and also by reducing the impact on our environment, reducing the consumption of energy and the emissions of CO2. And the use of the SCMs, these mineral admixtures, does that. The materials in category 3 above encompass finely divided materials such as, just to be this non-reactive material, this basically encompass finely divided materials such as ground limestone, silica flour, and hydrated lime, etc., materials of that sort. Although classed as non-reactive, some may weakly react with cement under certain conditions. These substances are basically blended with Portland cement to make masonry cements, with improved workability and water retention. If you remember when I talked about the cement types, we talked about the masonry cement. So this is one of the ways to make the masonry cement, by using these products. As we said, since the improved workability is the main use of these fine substances, they are also referred to as workability aids. Okay. Color pigments are also included in this category. Okay, so since these products are not really of much benefit in terms of being as supplementary cementitious materials, we will confine our discussion to the pozzolanic and cementitious materials. First, considering the different classes of these materials, and then the use of blended cements after that. So let's look at the history and origins of these materials. The addition of naturally occurring materials of volcanic origin to hydraulic limes was known to the Greeks. If you remember when I talked about the history of the cement, how Portland cement developed, I mentioned that. So Greeks used a volcanic ash from the island of Santorin, material referred to as Santorin earth, in order to enhance the properties of whatever concrete or cement they produced. This same material, though, or similar material, was used, in the building of the Pantheon, as we mentioned before. Then after that, the Romans adopted and extended, the Greek technology using ash from a variety of sources from around their empire. The name pozzolan basically is a modification or a corruption of the name Pozzoli, which is a town in the Bay of Naples that was the source of a highly prized deposit of weathered ash or tuff from Mount Vesuvius. These also the mortar used in Smeaton's Eddystone Lighthouse, if you remember I talked about it, which contained pozzolan from near the modern city of Civitavecchia. If if I pronounced that correctly, if I spelled it correctly. The name pozzolan basically is applied to any reactive aluminosilicate material of either natural or industrial origin. The material must either occur in a finely divided state or to be ground to cement fineness in order to be used as a cement supplementary material. So let's look at more classification of these, the types of the SCMs and the classes the classification according to STM. We have first the natural, which is according to ASTM C618, class N. This one produced from natural mineral deposits. For example, volcanic ash or pumicite, diatomaceous earth, paline, cherts, and shales. That's how it is produced. We have the processed manufactured SCMs or pozzolans, such as silica fume according to ASTM C1240, fly ash according to ASTM C215, and the slag, which is actually not exactly a pozzolanic material because it has some cementitious capabilities. This one according to ASTM C989. Let's talk more about the classification, pozzolanic materials, versus cementitious material. First, let's look at the pozzolanic material, which we have the highly pozzolanic materials such as silica fume, the metakaolin, and we have the rice husk ash. Of course, the rice husk ash, we have to be careful. There has to be controlled burning of this material in order to be suitable for the use in the concrete industry. We have under the pozzolanic material is the normally pozzolanic material such as the class F fly ash. We have also the second classification, which is the cementitious and pozzolanic material at the same time. This one, under this category, falls the slag, ground granulated blast furnace slag, and the class C fly ash. And of course, we have the purely cementitious material that's capable of being of having cementitious property or hardening on its own, such as the Portland cement. This diagram here, it shows really, put this in perspective, the classification of the material, which is basically based on their chemistry. If the material is high in silica, which is the amorphous silica, as we will see later, it will be more pozzolanic, which is, such natural pozzolans fall in this area. Silica fume is the highest because of its high reactive silica content. The type F fly ash falls here. Of course, it has higher silica, reactive silica content than the others. Ground granulated blast furnace slag, or just simply slag, and the type C fly ash are closer to the cementitious realm because of the lime content, their lime content, as we will see later. Of course, the Portland cement is purely cementitious material because it's of the high lime content. Okay. So, more about the pozzolanic versus hydraulic reaction, or the hydraulic material. This table here shows the different SCMs and how they react, whether they have the pozzolanic reactivity or hydraulic reactivity. Hydraulic meaning they have cementitious capability on their own. With the addition of water, they are capable of having cementitious tendencies. Of course, some materials, such as the slag, although they exhibit some hydrolicity, but they still may require an activator in order to exhibit cementitious property on its own. As you can see here, these materials, the first three, they're purely pozzolanic. Class C, fly ash, and slag, they exhibit both pozzolanic activity and hydraulic activity. And again, this is determined basically by the calcium content, which is very low for these three categories and gets higher as we get here. Slag is the highest amongst these. But again, I said this may require an activator in order to work. So let's look at the composition of these SCMs. Let's look at the first, the chemical composition or the chemical analysis. Okay, because pozzolans are, such diverse materials, it would be expected that, their overall chemical composition would be quite variable. And this is indeed the case, as I will show on the next slide here. For this reason, the ASTM specification C618 for fly ash and natural pozzolans is primarily as a performance specification. So a major provision of this, the ASTM specification, is called the minimum strength activity index, of 75%. We will talk about this a bit later. The activity index of 75% at 7 and 28 days as determined by ASTM C311. Basically, the index compares the cube compressive strength of mortar containing 20% pozzolan replacement of the cement with that of the control mix containing no pozzolan, just pure Portland cement. We make mortar cubes and replace it 20% with pozzolan, with the pozzolan material we are interested in, and we make the cubes. And we have to have a certain, the performance is based on having a certain, strength activity index of 75% at 7 and 28 days. Okay, although there is, a chemical requirement, that the sum of the major acidic oxide, the silicon dioxide, the aluminum oxide, the ferric oxide, where it must be less than 70% or 50% for Class C fly ash. However, this requirement, unrealistically assumes that all oxides are able to participate in the pozzolanic reaction. And of course, that's not entirely true because it is really determined by the reactive silica component. Okay, the slide I just, the table I talked about earlier about the chemical composition, the oxide composition, and you can see we have this low calcium fly ash and the high calcium or high calcium oxide fly ash. Basically, this is the Class C, I believe. This is the Class F. Look at higher, this is the type F. Look at it here. It has higher silica content. This one has lower silica content, but it has much higher calcium oxide content. Okay. The slag, of course, has the highest typically calcium content, and that's why it's classified as pozzolanic cementitious. Silica fume, look at it, is the highest silica content. Metakaolin also has fairly high silica content, but no calcium content, so it's not cementitious. So let's talk about the crystalline components. The crystalline components, what does it mean? Which, basically, this is the material that is not reactive and it will not basically do us any good as a pozzolanic activity. Basically, an overall chemical analysis, while helpful, does not adequately characterize a pozzolan. A good pozzolan should have a high fraction of reactive, glassy, or amorphous material. I mentioned that about the reactive material. Basically, this material is formed, by rapid cooling of a high temperature liquid, which inhibits crystallization. Okay? This ideal is approached in a good quality silica fume with up to 98% of amorphous silica. While fly ash and natural pozzolans generally contain, significant inert crystalline phases. Crystalline phases are not reactive and they will not participate in the pozzolanic reaction. The crystalline impurities basically are, can be identified by the X-ray diffraction, which typical patterns of are shown here. Okay, I will talk about them in a bit. The amorphous or the glassy fraction produces, basically a characteristic hump, as you can see on those next slide. The position of this hump, varies according to the calcium oxide content, which is basically the location of the peak based on the 2 theta. We talked about the XRD early in the class. Basically, the location of this will impact the location of the hump. The sharp peaks superimposed on the hump are used to identify crystalline phases. As we can see, here, are some XRD, X-ray diffraction patterns for class F fly ash, the class C fly ash, silica fumes, and the granulated slag. And we have shown here a poorly quenched slag to show the difference. We ended up with less amorphous content. Okay. The use of XRD can provide the information about the glass contents and the crystalline phases, as you can see. As you can see, the good quality class F fly ash have about 70 to 90% glass with, we have a quartz, molite, hematite, and magnetite as principal phases that crystallize basically from the glass on cooling. Almost all of the iron is contained in the latter 2 phases, in the hematite and the magnetite. Okay. The class C fly ashes contain quartz. As you can see, we have the free lime and combined lime, as you can see in this peak right here, and anhydrite, which is right here. Calcium, basically the calcium sulfate without the water. Differentiate this from the dihydrate, which is the calcium sulfate with 2 molecules of water. Some of the fly ashes may contain also, as you can see, the calcium aluminate sulfate. And maybe they will contain other phases such as the dicalcium silicate in some cases. And also maybe tricalcium aluminate, as you can see here in this, this peak. So these fly ashes, like the class C, as I said, they will show some cementitious tendency and will become hard on the addition of water. Whereas, other pozzolans do not react with water alone, such as the silica fume or the class F. But in general, cementitious class C fly ashes should not be used. I always did not specify them in my concrete. Basically, to avoid problems with the high water demand, early stiffening, or rapid setting because of the aluminate and the calcium oxide, the free lime content. Or in cases basically where we have issues with the sulfate attack because their alumina content, the C3A, as you can see here. So this one to be used with care. I did not specify it. Okay. Natural pozzolans, basically have more variable glass content ranging from 50 to 90%. The principal crystalline compounds are quartz and feldspar, but some, when we have volcanic tuffs or ash, they may contain other materials called zeolites, which, although this zeolite, although crystalline, it has some pozzolanic behaviors. Look, for example, here at the silica fume. You notice the large, this broad hump is indicating the large amorphous or reactive silica content with almost the absence of a clear crystalline peaks. Okay, so that's the good thing about silica fume. Notice here the difference between the granulated slag and the poorly quenched slag. Look at when the case of the granulated slag, this diffuse band, the large hump indicating reactive or amorphous silica, versus this one where it has many crystalline product. Of course, is going to be less reactive than this one. Okay, so quenching of certain SCMs like the slag is key in order to ensure that we end up with reactive or amorphous material that will be reactive. Okay, so basically this slide here shows what I just discussed, the summary of what I just discussed. Although, we talked about these major, and the chemical composition, we talked about these major components. Also, you have to be careful of some of the minor components that might be present and some of these SCMs. There are in few cases, many pozzolans may contain alkali oxides or alkalis, and we talked about these before. In the case of fly ash, these are often, in the form of soluble salts that have been intentionally added to improve the efficiency of electrostatic precipitators, as you will see during the process. And they may occasionally influence the rate of setting. So that's something you have to be aware of. In the case of natural pozzolans, the alkalis are usually in an insoluble form and are released only during reactions, if at all. So since pozzolans are added to control the alkali aggregate reactions, as we will see later, the addition of more alkali is basically counterproductive. So you have to be careful. So if pozzolans are to be used for the purpose of the alkali, for this purpose to counteract or to mitigate the alkali aggregate reactions, alkali content should be determined so that its contribution to the total alkalis of the concrete can be calculated. So that's, again, something you have to be aware of. You get the mill certificate or whatever pozzolan is being used in order to make sure it does not add harmful material to your concrete mix. Also, many of the byproduct materials, contain unburned carbon. About 1 to 2% for the silica fume, maybe 0.5 to 3% for fly ashes, but sometimes could reach as high as 25%. So you have to be careful. Or maybe 3 to 18% for the rice husk ash. This high carbon content in some fly ashes can be reduced to low level using electrostatic separators to make them more suitable for the use in concrete. Of course, if it has this high level of carbon, we cannot use it. The high level of carbon in many rice husk ashes basically has inhibited the large-scale commercial use of this material. despite its high pozzolanic activity. As you can see, it has high pozzolanic activity, but if it's not controlled, the process of it, then it cannot be used. We have, sometimes, specially designed furnaces to be used to completely remove residual carbon from decomposing cellulose, in that case at low enough temperature so that the amorphous silica will not crystallize. That's again another aspect that you have to be aware of. Okay, what's the harm, of the carbon content? The main concern about residual carbon is its detrimental effects on air entrainment, as we will see when we discuss the chemical admixtures. Usually, higher doses of air entraining agents will be required, and in some extreme cases, satisfactory air entrainment may not be possible with the high carbon content. Carbon also affects the color of the ash, although iron contents are also important in this regard, so that's why, pozzolans may range in color from very light off-white shades to almost black. Look back at the the photo I showed at the beginning of this lecture. So for this case, how to determine, the carbon limits. ASTM C618 basically sets limits for carbon, which is determined, basically estimated from the loss on ignition. So ASTM C618 sets limits for this carbon, through loss on ignition. And there are optional limits, on the amount of alkalis. This is left up to the engineer, as a performance-based specifications to make sure higher alkali is harmful to your concrete mix. You have to act. Also, ASTM C618 basically restricts the amount of SO3 and, also reduces the chances of unsoundness due to the hydration of the barricades. You remember we talked about the soundness, or the unsoundness due to the late reaction of the magnesium oxide, which will be expansive and will result in cracking. So ASTM C618 put limit on this, and basically through the autoclave expansion test. Okay, so let's look at the physical characteristics of these SCMs. Pozzolan must be in a finely divided state to be effective. Okay? Most natural materials require grinding to cement fineness in order to be declared fit for use. But the industrial byproducts often exist, as fine particles and need not be ground. A comparison of some of the materials, shown in the table. I will talk about it in a minute on the next slide. It can be seen, that the particle morphology is highly variable, as you can see here. We will talk about it. Spherical particles are highly desirable because they have positive impact on workability, while cellular and platy particles impart higher water demand for workability. The ASTM C618 limits the amount of material retained on the 45 micron mesh, which is the number 325 sieve basically. But this really is an inadequate assessment of the particle size and shape. It does not give an indication of the particle size distribution. So the more useful parameter is the surface area, since the rate of pozzolanic reaction will be proportional to the amount of surface available for reaction. The high surface area of the rice husk ash in relation to its mean particle size, Usually this is consequence of its cellular nature, and this is the reason for its high reactivity, but also results in basically in high water demand, as you can see here. Basically this is, as I said, its mean particle size is a consequence, of this reason. Okay, so this is this one here shows you basically a comparison, the Portland cement as a reference. We have the mean size of the particles, 10 to 15 micron, surface area, meter square per gram, less than 1 here, less than 1 for the natural pozzolans. Shape is again angular, irregular, similar. The fly ash CNF is comparable to concrete. Surface area is higher. The spherical shape helps workability. Specific gravity less than cement. Silica fume, the particle size is way smaller, mean particle size. That's why it has a good packing characteristic in making sure we have denser concrete matrix. Surface area is much higher, spherical shape. The rice husk ash, although as I said, the surface area is really high in relation to its mean. The mean size is not much, is larger rather, is larger than, for example, silica fume. But the high surface area, as I said, is a consequence of the cellular nature for its cellular nature. And as I said, this is the reason for its high reactivity. Okay, we have the calcined clay or the metakaolin. The mean size, of course, is very small compared to the Portland cement. The surface area is higher, much higher, of course. The particle shape is platy. Okay, so we need, a complete particle size distribution analysis in order to be even more useful, and comparisons, for this are shown in the next slide I will talk about, which basically here it shows how these SCMs compare to one another and how they compare to the cement. Okay, sorry, let me go back. For example, let's look at this, the silica fume. The extremely, fine nature of the silica fume is very evident, and this is the reason for its high activity, as we mentioned. However, such a fine material is very difficult to handle. You have to keep in mind it becomes very sticky if you use it as powder, and something has to be done. So the silica fume is generally supplied in more easily handled forms, such as, either slurry in water or more commonly in a densified state. So in this case, the material is mechanically agglomerated, and these agglomerates should be redispersed in the concrete mixture in order to be useful. If nearly complete dispersion is not achieved, much of the benefits of adding silica fume will be lost. Okay, but it is not unusual to find some large agglomerated particles that have not been dispersed. So I said, really, using silica fume in the concrete, it has to be done with care and with certain methodology to make sure we get full benefits of it. But as I said, the benefits of the very fine nature of the silica fume is its ability to pack between the cement particles. This particle packing characteristic sets it apart from other pozzolans. Although it can be achieved to some extent with calcined clays, particle packing reduces bleeding, lowers the mean size of the capillary pores. And you remember, you go back to the microstructure of the cement paste. It reduces, lowers the mean size of the capillary pores, and if used correctly, can reduce the water requirements. Okay. Replacement between 5 to 10% by massive cement is required to provide significant effects. Maybe, of course, we need to use water reducing agent in order to disperse, both silica fume and cement. When we use silica fume, water reducing agents need to be used. With this combination, though, the silica fume and the water reducing agent, water cementitious material ratio as low as 0.25 can be achieved while maintaining good flowability. Of course, the benefit to the concrete durability is superb. Okay. So basically, let me go back to this slide. We talked about the silica fume because really it's the most significant in terms of the particle size distribution. As I said, calcined clay to a certain extent can give the same, which is the metakaolin, can give the same benefit of silica fume. But like I said, the packing, the particle packing characteristic of it really sets it apart from the others, the fly ash basically. Okay. Okay, so let's see, just generally see what benefits can we get from the SCMs in terms of improving the concrete properties. Many of the effects, the beneficial effects of using the SCMs are related to the effect they have on the pore structure. We said refined, densified cement paste matrix, and one of the benefits is the refined, the effect on the pore structure. By doing this, it works as microfiller effect, basically increased packing of cementitious particles. We have increased calcium silicate hydrate. Remember what we said during the hydration lectures. Calcium silicate hydrate is responsible for the strength. Calcium hydroxide has problems, leaching, acid attack, and eventually, an increased permeability. So basically what we do, we increase the calcium silicate hydrate, get rid of the calcium hydroxide, which has many drawbacks. So basically it's a double advantage. We also have something called the wall effect. Basically what this is, densifying the interfacial transition zone I talked about earlier. Basically at the cement paste aggregate interface, where we said this is more porous, less dense zone. So the use of the SCMs help us improve this zone. We have also the pore blocking, which basically occurs because of combination of these factors together. The above factors, basically the above effects, refine the pore structure and reduce the permeability of the concrete. By this, they are making it more resistant to the penetration of the deleterious agents. So this is just a general synopsis of what they do. Of course, toward the end of this, maybe the second or the third lecture of this series of lectures, we will talk in more details about their benefit to concrete, but this is just the general presentation. Okay, this is here the end of the lecture 16, and in the next lecture, lecture 17, we will continue the discussions we will continue our discussion on the SCMs. Until then, thank you for watching, and we'll see you next time.